We're going to do more practice with U-Substitution. What kind of integrals were we taking yesterday? We were undoing the chain rule by doing U-Substitution, but what type of integrals? Indefinite. Why was it indefinite? There was no bounds, right? So our end result was a function, right? So today we're going to focus on using U-Substitution to find the definite integral. In other words, to evaluate areas or net areas of more complicated functions. Are we good with that? Can I go on? No? I can apply U-Substitution to evaluate a definite integral. There's two ways to approach it. The first way is the way that I kind of learned it. And the reason I learned it that way is because it's probably the easier way for me to see it, but it's not the greatest way because it's a mix and match of two different things, and it's not necessarily the best. But I'll show it to you anyways so that you can compare it to the other way. Okay? We just did an example of U-Substitution. So we know how to do it if it's an indefinite integral. For a definite integral, what kind of answer are we going to get? A number. We're going to get a numeric value. So let's look at the first way. This is going to seem weird to you. I'll give you an example in a second. The first way is to do exactly what you did before. Evaluate the integral using U-Substitution. And then when you're all said and done, what do you do on the last step? No, not on the integral itself, but in U-Substitution, what's the very last step of U-Substitution? Yeah, replace the x's back into the equation, so it's in terms of x, right? And then from there, we evaluate the definite integral like we always do. So let's look at a very easy example, hopefully. We'll do option 1 using this example. Let's say the integral of 2x squared dx from 2 to 3. Now you can simplify that. You don't have to use U-Substitution, but just for the sake of practice, what's the good u value? So u equals 2x. So du dx equals 2. And then what do we do now? Get dx by itself, right? So multiply by dx, and then we're going to divide by 2. So we get 1/2 du equals dx. You guys okay with that? Then we're going to plug in our values. What's that? So instead of 2x, it's going to be u squared times 1/2 du. And the integral, right? Okay. Move the 1/2 out. So you got 1/2 u squared du. What do you get? What's the antiderivative 1/2 u squared? U to the third. Remember, the 1/2 can go outside, right? So just what's the antiderivative of u squared? 1/3. Now bring the 1/2 back in. 1/6, right? What kind of integral is that? Indefinite, so I'm going to put a plus c there, right? What's the next step? Plug in so you get 1/6 times 2x cubed plus c, right? Now this was a definite integral, so now what? Evaluate at your points, right? What were our points? 2 and 3. And when we go from there, we'll get 1/6 2 times 3 cubed minus, 1/6. 1/6 2 times 2 cubed. True, but the original problem was a definite. So I would ask this question: why did I not put my bounds here as I went along? Maybe just kind of keep things clean. The notation isn't the best on this, but here's why. Remember what the rule was. The end result, before I actually took the antiderivative, what did this have to say? That. Okay. Everything had to be in terms of u, right? You couldn't have any x's left, right? You can't have x, dx, or anything, right? That'd be all in terms of u. What do the limits mean in a definite integral? From this point to this point, we're finding the net area, right? What kind of values are those? They're x values. So I can't use 2 and 3 because those are x values when I have a u function. Does that make sense? So I didn't consider those limits here. I only reconsidered them when I had my function back in terms of x. Does that make sense? Okay. So that's option 1. Option 2 is to basically do the same thing, but reevaluate your limits. So instead of having your limits in terms of x, we're going to put our limits in terms of u. And I'll call this ultimate substitution. So there's U-Substitution, and there's ultimate substitution. Ooh. In other words, we're not just replacing the x's and the dx's. We're placing the x's, the dx's, and the limits, right? The upper and lower limit. Does that make sense? Yeah, okay. So we're going to reevaluate the upper and lower limits. How do we do that, though? We want it in respect to u. How are we going to do that? We're going to do the same steps. U equals 2x, du dx equals 2, and as a result, 1/2 du equals dx. The integral would then be u squared, sorry, I'll just skip that step, 1/2 u squared du, right? But I still want this to be a definite integral, right? So I've got to figure out what values will go there. If I plug in 2 and 3, those are what kind of values? X values. So how do I get u values from the x values? So let's do this. The lower bound, let's just focus on the lower bound. What is the x value of the lower bound? 2. So what would the u value be? U on the lower bound is equal to what? U is equal to 2x. So u is equal to 2 times, what's the lower bound? 2. So it's 4. And the upper bound would be 6. So u equals 2 times the upper bound, the x value, so 6. So now our lower bound is 4 and 6. You guys okay with that? Okay. And then now we evaluate it the same way we did before. Antiderivative is 1/6 u cubed, evaluated from 4 to 6. We don't need the plus c because it's definite integral. And I don't have to go back to replacing it with x because my limits are in terms of u now. So what do we get? 1/6 6 to the third minus 1/6 4 to the third. Yeah, because look, 6 is the same as 2 times 3, right? And 4 is the same as 2 times 2. Are you guys okay with that? So I kind of understood it this way when I was learning it. It's like I don't like you. You guys don't like you, right? I don't like you. That's just, you know, anyways. Yeah. See how funny I am? I don't even mean to be, and it just works. Yeah. I didn't say us. I said you.
If you don't like anyone in here, keep that in the video.
All right. So I didn't like dealing with you. So I've got. How can I do this? How can I say this? Okay. So I worked with it until I got down to a point, and then I put it back in terms of x because I like x. Okay. But how do you think the AP exam asks questions? This way. Because technically the notation here doesn't make sense. What kind of integral were we trying to evaluate? A definite. And here I'm working with indefinite. So really the notation doesn't work. And you can't put limits in here. You can't put the same limits because they're not x values anymore. They're u values. So they test like this. So oftentimes, here's an example of this. They'll say, what is that equivalent to? They'll say, option A. Which one of these is true? Option A. The integral of 1/2 u squared du from 2 to 3. Is that the same as that? Where did this come from? It's this thing, right? It's replacing U-Substitution, but what's wrong? These are what kind of limits? X limits, and this is a u function, right? So you would say, well, that's not true. And then they might do something like this. They might say the integral of 2x squared dx from 4 to 6. The function's in terms of x, but the limits are in terms of u. And so then they'll give you the option of 4 to 6 of 1/2 u squared du. So now the function's in terms of u, the limits are in terms of u, so we're good to go. Does that make sense? So it's just good practice to do ultimate substitution. Okay? And again, like I just said, this is how the tests are written. Okay? Give this a try, or do you want me to do it?
We want you to do it.
Oh, be quiet. I'm not going to do it.
You just typed it in and left it as. I didn't want you to erase that at all.
We're going to do it right now. Okay. So we have the integral from 0 to 1 of x over x squared minus 4 dx. When you're doing u substitution, especially at the beginning, you just guess something. You try something. So let's just say, for the heck of it, let u equal x. That isn't going to do a thing for us because these basically have the same power, right? U and x, that's not going to be beneficial. But for the sake of argument, du dx is what? 1. So du equals dx, right? Now we'll go substitute. What goes on top? U over, anything replace that? So x squared minus 4. You could say u squared minus 4 if you want. Du, right? But did that make it so I could evaluate it? No, because I have u's and x's. So that's why sometimes you try a u, it doesn't work, you try another u. So u equals, what's a good one? You see, if you say x squared minus 4, that's fine, but when you go to substitute, what's going to be in the bottom? It'll be u. If I just say u is x squared, it's going to say u minus 4, right? And that's kind of a pain. So let's just say x squared minus 4. What's the derivative then? 2x. And you see the derivative of negative 4 just made it, it's the same thing anyway, so it went away. So solving for dx, you get dx equals 1 over 2x du. Right? Now, rewrite it. So what goes on top? X over u, okay, x over u times 1 over 2x du. That's not acceptable because you have multiple variables, but the x is reduced, so you're left with the integral of 1 over 2u du, right? You guys okay with that? Now, this is not acceptable, so I'm just going to cross that out and go with that. But what do I have to do now? I got to find my new upper limit and my new lower limit. So how do I find my upper limit? U equals x squared minus 4, so 1 squared minus 4, which is negative 3. And then lower limit will be u equals 0 squared minus 4, which is negative 4. So my integral is from negative 4 to negative 3. Sometimes these will be flip-flopped. Just make sure when you plugged in the lower value, whatever you get when you plug in the lower value goes on the bottom. Whatever you plug in for the upper value goes on top. But we haven't taken the antiderivative yet. Any questions so far? This is where it gets interesting. I'm going to blow your mind right now.
Probably not.
You ready? Watch this. How would you take the antiderivative? There's no quotient rule. Okay, I could rewrite this as 1/2 times 1 over u du. Agreed? Because that's a constant, that makes life easier, right? So what do you get? 1/2 natural log of. Here's why the absolute value is critical. Because when I go to plug in the negative 4 and the negative 3, if I plug in negative 3, what's the natural log of negative 3? That doesn't exist. You can't take the natural log of a negative number. So we put the absolute values there to fix that, and we'll address more about why that's okay later. So you end up with 1/2 of the natural log of the absolute value of negative 3 minus 1/2 times the natural log of the absolute value of negative 4 which is, what can I do to simplify that? Okay, 1/2 times the natural log of 3 minus the natural log of 4. You guys okay with that? What's the rule? What's the rule in logs? Quotient. So what's it going to say? 3/4. You guys okay with that? That's a log rule from Algebra 2. If you're subtracting with the same base, this has the same base of e, then it's the natural log or the log or whatever of the first divided by the second. Now hold on, that's not the part that was supposed to go. Watch this. Here, I'm going to reevaluate this integral differently. Would you agree? Would you agree? See if you agree with me. Is that the same? Is that the antiderivative of that? I didn't factor out the 1/2 to start. Take the derivative, see what you get. What would you get if you take the derivative? 1/2 times 1/2u times 2. 1/2u. Agreed? Because I can. My point is, wait a minute. Do you agree that this is the antiderivative to that? I just did the work to show you the derivative of this is that, right? Okay. Now I'm going to evaluate from -4 to -3. What I'm essentially saying here, this is interesting, am I really saying that this antiderivative, 1/2 of natural log of absolute value of u, is equal to this antiderivative? In order for these to be equal to each other, what would have to be the case? 1/2 is the same as 1/2, right? Natural log is the same as natural log. We'd have to say that 2u has to equal u. Does 2u always equal u? No. So are these the same function? No, they're not. But wait. Wait. 1/2 of the natural log of, let's plug in now, 2 times -3 minus 1/2 of the natural log of 2 times -4. So we get 1/2, factor that out, you get natural log of 6 minus the natural log of 8. So it's 1/2 natural log of 6/8. Same thing, right? Why did that work? Well, yeah, because I can reduce it, sure. But why is this an antiderivative and that's an antiderivative, but they're not the same thing? Remember, we're taking the definite integral, right? We're taking the definite integral, so we're not saying that these two functions are the same function. We're saying when I evaluate these functions with these values in them, it ends up being the same result, coincidentally. If there was no limits, then we'd have to say that this is the same as this. Yes? No. Because if there's no limits, what kind of integral is this? It's indefinite, which means, what's the antiderivative here? Plus c, 1/2 of the natural log of the absolute value of 2u, plus c, kind of. This is a constant, right? This is a constant. They don't have to be the same constant. This could be a different constant. Right? If these constants are different, then these functions can be the same. Do you agree with me that these are not the same? That's not the same. Is it? No. So if I can add something to this and add something else, something different to that, can I make them the same? They aren't the same, but they're different only by a constant value. Okay? The point is mute. Did you get the antiderivative? Did you get it? Did you get it? Or did you do it this way? The end result is the same. Right? That's for you to ponder for a while. Yes? How'd I get the what? So I took the original limits of 0 and 1. My upper limit, remember, this is an x value. So I had to plug in the x value into my u equation to get my new u value. Yeah, because otherwise your limits are in terms of x, but your function's in terms of u. That doesn't make sense. All right. All right, you guys try these. Oh. Complain. Big numbers. Big equations. All right, if you want to deal with little equations and little numbers, go get a job at, McDonald's and deal with little things, little problems in life.
But Mr. Money, what if they want to know the rate at which they can make hamburgers? Then it'll come in handy.
Actually, that is a very big concern of McDonald's in terms of finances. If I know how quickly one employee can make hamburgers, I can calculate how many employees I need, number one. And number two, if my machine can do it faster, for cheaper, and his rate, that rate is greater than this one, I'm going to fire my employee and hire a machine. Dead serious. Dead serious. So you better be good at flipping hamburgers, or you better be good at calculus, one of the two. Remember, we are undoing what rule here? We're undoing chain rule. So the end result of the chain rule is a product. The product is the derivative of one thing times the derivative of another. So when you identify your u, when you go to take the derivative of that, it should match something that's there. There's a couple different ways of doing this, and you guys are about 50-50 on how you're going to approach it, and that's great. No, it really is, because it shows you math actually works. All right, person number one may have said that u equals what? Tangent x? Okay. Then du dx equals secant squared x. How do you know that you might be on the right track? Because you got tangent x and secant squared x in there, right? So that's good. So watch this. I'm going to shortcut this a little bit. Hopefully intuitively you can see it. You see how du equals just secant squared x dx? Secant squared x dx is already there. So I could solve for dx, and that's fine, and you'll see the secants cancel out. But I'm just going to replace it right now. The integral of, what's tangent x? U times secant squared x dx is just du. You guys okay with that? Yeah. What else do I have to do?
Upper and lower limit.
Okay. Upper and lower limits. So let's do the upper limit. U equals what? Tangent of? No. Upper limit. Pi over 3. What's the tangent of pi over 3? Is it rad 3? Okay. And the lower limit is u equals tangent of 0, which is 0. So we got 0 to rad 3. All right. What's the antiderivative? U squared evaluated from 0 to rad 3. So we say 1/2 of rad 3 squared minus 1/2 of 0 squared. So 3/2 altogether. Are we okay with that? The antiderivative of u. Remember, what's the rule? You add 1 to the power, and you got to divide by. Now, person 2 might have said, let u equal secant x. Secant squared wouldn't have worked. Because the derivative of secant squared would have been 2 secant x times secant x tangent x over gross. What's du dx? Secant x tangent x. Do you see those things over there? Yeah. Let me rewrite this. The integral of from 0 to pi over 3 of tangent x, well, actually, let me rewrite it like this. Secant x times tangent x x dx. Do you agree that that's what that was? Tangent x secant squared x is the same as this, yeah? Okay. What's secant x then? U. What's secant tangent dx? du. Wait a minute. What do we have to do with the limits? Are they going to be the same upper and lower limits? No, because my u is a different function, right? So let's see. What's my upper limit? U equals secant of pi over 3. What is secant of pi over 3? What's cosine of pi over 3? 1/2. So secant is the reciprocal, right? 2. And the lower? U equals a secant of 0. Wait a minute. What's secant of 0? What's cosine of 0? 1. Reciprocal is 1. So it's from what to what? 1 to 2. Okay. Antiderivative? 1/2 u squared from 1 to 2. So that's 1/2 of 2 squared minus 1/2 of 1 squared. So that's what? 2 minus 1/2, which is 3/2.
I knew that was going to happen.
If math doesn't work, it might not.
Math always works.
That's right. All right. Next year.
I know, next year's going to have a ball game.
So ultimate substitution, yes, I made that up.
Definitely not.
But it is U-Substitution. Okay, so let's try this. One more, huh? R changes everything. What is a good U for the first one? If you had a constant in there, throw the constant in there with it. So what's a good U? 1 minus r squared. What's a good U on number 2? 4 plus r squared. You guys okay with that?